Welcome to AI Paper Slop, especially if you are an AI researcher or ML engineer tuning in today. We are jumping straight into a paper that, honestly, it challenges the biggest default assumption in our field, which is that foundation models absolutely have to be pre-trained on text-only representations.
Yeah, it's a pretty massive paradigm shift. The paper is called Scalable Visual Pretraining for Language Intelligence, and it comes from the Shanghai AI Lab and their collaborator.
Right, and they essentially proved you can train directly on raw visual documents. We were talking about raw PDFs of scientific papers, just, skipping the text extraction entirely.
Exactly. They used an autoregressive visual latent prediction objective. And the craziest part is that it actually achieves stronger language intelligence and scientific reasoning than the standard text-only baseline.
Which is wild. And it does this using only 25% of the token budget. Plus, it naturally aligns the text and visual modalities without a single piece of explicit image-text paired supervision.
I mean, zero paired data. You get all that alignment completely for free.
So our mission today is to unpack exactly how they built this visual pre-training pathway, like why text extraction is inherently lossy, the actual mechanics of predicting continuous visual latents, and, well, what this means for scaling multimodal foundation models moving forward.
You really have to realize we've been basically starving our models of critical structural information just by clinging to this text-first paradigm.
Let's start right there, actually. What are we losing when we take a scientific PDF and just, turn it into text? Because if you're an ML engineer parsing data, you're probably using tools like NuGet or MinerU.
Right, and those tools are great for what they do, but they flatten reality. You take this beautifully formatted paper with math and charts and you squash it into this 1D string of latex or markdown.
It's just a massive wall of text tokens.
Exactly.
Yeah.
But a scientific paper uses spatial layout to communicate actual meaning. Like the way a formula sits next to a diagram or the geometric constraints of a table, that is all data.
Yeah, the topological relationship between, say, a paragraph and a specific axis on a chart.
Yes. When MinerU strips that out to give you a clean text sequence, it is literally deleting the spatial correspondence that makes the logic cohere in the first place.
It reminds me of trying to describe a complex architectural blueprint over a phone call to a contractor. You're forced to read out these spatial dimensions sequentially. Like, okay, the load-bearing beam intersects the wall 3 feet from the corner.
Oh, that sounds agonizing.
Right. It's terrible. You lose all those immediate spatial relationships that make the blueprint instantly logical the second you look at it.
Yeah.
And we force our AI models to learn through that exact same agonizing phone call.
And cognitive science actually backs up why that is so horribly inefficient. The authors invoke the Platonic representation hypothesis here.
Which is the idea that intelligent systems eventually converge on shared abstract representations of reality, right?
Exactly. Whether it's human brains or neural networks, humans do not reason exclusively in a linear stream of words. We use spatial mapping. We use diagrams. Those visual cues let us infer relationships instantly.
So by bottlenecking a visually rich PDF into a linear text sequence, the model is really only getting like a shadow of the actual knowledge on the page.
Right, but that obviously brings up a huge engineering hurdle. We know raw pixels hold the structure, but how do you train a language model directly on the visual page without your compute budget just catching fire?
Yeah, you can't just shove an entire high-resolution PDF into a context window as raw pixels. That's a complete non-starter.
The context link would absolutely explode. So they designed this remarkably elegant decoder-free architecture to get around it. Basically, a raw document page goes through a frozen vision transformer, a VIT encoder.
Okay, so the VIT extracts visual features and breaks the page down into a grid of patches.
Right, but they don't feed that entire grid to the LLM.
Because most of a PDF is just blank white space, I'm guessing, like the margins and the gaps between paragraphs.
Exactly. Well, they are highly specific about how they drop that white space. They use foreground filtering based on 2 metrics pixel variance and average luminance.
Let me make sure I'm tracking the math on that. So high luminance means it's bright, which means a white background, and near zero variance means there's no change in the pixels, so no letters or lines.
Spot on. The model calculates the variance and luminance for every single patch, and if a patch hits that threshold of being basically flat white, it's dynamically masked out, just completely thrown away.
Oh, wow. So that drastically cuts down the sequence length right there.
Hugely. The patches that actually survive, the foreground patches with the equations, the text, the figures, they are then packed tightly together. They use a raster scan order, so just reading them left to right, top to bottom.
So you end up with this tightly packed sequence of dense visual features. And then those are linearly projected straight into the LLM's hidden space.
Yep. But here is the major technical pivot that we really need to pull apart: the objective function itself.
Right, because in standard LLM pre-training, you're predicting the next discrete text token from a fixed vocabulary. You have an exact, known right answer. But here, they are predicting the next continuous visual latent.
Using standard causal attention, just like it was text.
But wait, hold on. If it's predicting continuous latents, how do they avoid representation collapse? I mean, this is the classic trap, right?
It absolutely is.
If I have a network predicting a continuous vector, the absolute laziest, easiest way for it to minimize a mean squared error loss is to just output the exact same blurry average vector every single time. It basically just guesses gray and the loss drops. So how is it learning anything?
Well, it would completely collapse if they used mean squared error. They avoid that trap by using an InfoNCE contrastive loss instead. That's really the secret sauce of this whole training objective.
Okay, unpack the InfoNCE loss for me. How does it stop the model from just blurring everything?
So think about what contrastive learning forces the model to do. For every position in that raster stand sequence, the model isn't just trying to get numerically close to the target vector. The InfoNCE loss demands that the model's prediction must match the true next foreground patch, while simultaneously pushing its prediction far away from all the other visual features in that exact same batch.
Ah, I see. So all the other patches in the batch act as negative examples.
Exactly. They are the negative samples in the denominator of the loss function. The model has to actively distinguish the true next patch, say the second half of a physics equation, from a patch containing a pie chart or a patch with abstract text, all sitting in the same batch.
So to minimize the loss, it literally must capture precise semantic and structural details. It can't just output an average vector, because an average vector would be equally close to all the negative samples.
Right. The loss would just skyrocket. It's forced to learn the specific granular meaning of the patch to tell it apart from the rest of the page. And, they aren't doing this in a vacuum.
Right. They interleave this visual pre-training with standard text cross-entropy loss.
Yeah, it's a joint training process. So the model sees text documents where it predicts the next discrete word, and it sees raw visual PDFs where it predicts the next continuous visual latent.
Sharing the same underlying LLM backbone. It's basically building the visual reasoning on top of the text foundation.
Exactly. Which actually brings us to the compute math, which I know you'll love.
Yeah, because as an engineer, you hear vision models and continuous latents, and you immediately assume this is going to cost an absolute fortune in compute.
But it doesn't. The paper claims it's actually more efficient than the standard text parsing baseline.
Wait, really? How much more efficient?
The token savings are staggering. They trained on the exact same corpus of scientific PDFs. The baseline approach, running all those PDFs through a parser to get text yielded roughly 80 billion text tokens.
Okay, 80 billion.
But the visual pre-training pathway, using that foreground filtering we just talked about, compressed that exact same knowledge in just 20 billion visual tokens.
That is a 75% reduction in tokens. It's like the visual tokens act as a highly compressed zip file for knowledge.
That is a perfect way to describe it.
Because if you think about writing out a massive Navier-Stokes equation in LaTeX, you need a distinct, discrete token for every underscore, every bracket, every fraction bar, every single Greek letter. It might take 50 or 60 tokens for just one equation.
Right. But rendered visually, that entire equation might just be 2 or 3 dense visual patches. The spatial arrangement compresses the information.
And does that compression actually hold up during the later training stages?
It does. You can see the impact during the supervised fine-tuning stage, the SFT stage. The model that underwent visual pre-training converges significantly faster, and it hits a lower final loss than the text-only pre-trained model.
So the visual representations are just prepping the network better for structured reasoning tasks. And they actually quantified that structural advantage, right? With something they called visual structure density.
Yeah, they did, and it proves your zip file analogy perfectly. They stratified their test sets to see where the model was really gaining its edge. When they looked at low-density pages, so pages that are mostly just continuous paragraphs of plain prose, the visual pre-training and text pre-training performed pretty much identically.
Which makes sense, because text isn't the lossy format for basic prose.
Exactly.
Yeah.
But when they evaluated performance on high-density pages, the ones just crammed with geometric figures, complex math matrices, and tables, the visual pre-training totally blew the text baseline out of the water.
Wow, so the performance gains literally scale in direct proportion to how visually dense the underlying information is.
Yes, exactly.
But there's a massive caveat here that I found really fascinating. More is not always better. They did a sweep on the visual token budget to see how far they could push this, and they hit a really hard wall.
Yeah, they found a very rigid sweet spot. When they scaled the visual token budget within their fixed training context, they found that retaining exactly 8,192 foreground tokens per batch yielded the absolute best downstream performance.
They call this the 1x setting in the paper. But if I have a bigger GPU, why wouldn't I just shove 16,000 or 32,000 visual tokens into the batch? Wouldn't more data make it smarter?
You would think so, but pushing more visual tokens actually degraded the model's reasoning capabilities. And the reason comes right back to the mechanics of that InfoNCE contrastive loss we were talking about.
How does the token count break the loss function?
So remember that every other visual token in the batch acts as a negative sample. The contrastive loss uses a softmax function over all of those samples. As you cram more and more visual tokens into the batch, the denominator in that softmax gets incredibly large and crowded.
Oh, I see. Because you are introducing tens of thousands of negative samples all at once.
Exactly. It fundamentally alters the optimization dynamics. The effective gradient scale shrinks, and the model struggles to map out the contrastive landscape because every single prediction target is just buried under this massive avalanche of negatives.
So by capping it at exactly 8,192 tokens, they stabilize those learning dynamics so the gradients can actually guide the model effectively. That is such a crucial engineering detail.
It really is. You can't just blindly scale the batch size when you're working with contrastive latents.
Let's pivot slightly to what this efficiently trained model can actually do, because the cross-modal alignment results look basically like magic. It feels like they got a multimodal free lunch.
Free lunch is the exact right phrase for it. Let's recap the setup just to appreciate how strange this actually is. The model is trained on text documents. It is separately trained on visual documents. At no point, literally zero explicit supervision, do the researchers feed the model a picture of an apple next to the word apple.
Right, there's absolutely no paired image-text data in the pipeline.
None. Yet when you look at the hidden space, the text and visual modalities perfectly align. They ran the centroid separation metric, which is just measuring the distance between the center of the text embeddings and the center of the image embeddings, and it dropped from 1.665 down to 0.661.
That is a massive jump. They also measured this using linear CKA, right? Centered kernel alignment.
Yep. Think of CKA as a way to measure whether the shape of the model's internal representations are similar across different data types. So if the model processes a text equation and a visual equation, does the neural activity follow the same geometric pattern?
And the CKA improved significantly, meaning the structural geometry of those two spaces essentially merged. But I am genuinely stuck on the why here. Without paired data, how does the optimizer know that the visual patch of an integral sign belongs in the exact same latent neighborhood as the text word integral?
It all comes down to the shared predictive task. Both the text pathway and the visual pathway are fundamentally trying to predict the next logical step in a scientific paper.
Okay, I follow.
Because the underlying physics and math are identical regardless of the medium, the logical reasoning steps required to predict that next token or patch are also identical. The optimizer simply discovers that the most efficient way to minimize loss across both modalities is to route them through the exact same internal reasoning pathways.
It clusters them together because the semantic function is exactly the same. The logic essentially forces the alignment.
Exactly.
That actually makes their generative image-to-text retrieval test make a lot more sense. They tested conditional perplexity to see if the model could retrieve text based on an image, despite never being trained for retrieval at all.
And the results were insane. The recall at 1, meaning its very first guess, was the perfectly correct match jumped from 64% to 99%.
It basically became a flawless retrieval engine by complete accident.
And this alignment translates directly to state-of-the-art performance on the hardest reasoning benchmarks we currently have. We're talking GPQA Diamond, which tests graduate-level reasoning, and AIM-25 for elite math competitions.
And on the visual side, it crushed the baselines on MMU Pro, Chartier Pro, and MathVista.
Yeah.
But the proof of how it actually solves those benchmarks is buried in Figure 4 of the paper, and it is honestly my favorite part of this entire study.
The attention map analysis, it's so good.
They fed the model a complex math problem in 2 different formats, plain text and a visual image of the exact same problem.
And when they tracked where the model was allocating its attention to generate the final answer, the heat maps were practically identical in their semantic focus.
Right. The text model's attention highlights the constraints of the math problem and the intermediate steps, mostly ignoring the filler words. And when you look at the visual model's attention map, it is highlighting the exact same semantic evidence.
The visual tokens generating the answer are actively looking at the visual patches that contain the constraints and the intermediate equations. It completely ignores all the visual white space and the filler text patches.
The question for you on this: if the attention maps are highlighting the same semantic evidence, does that mean the LLM is literally running the exact same internal thinking circuit at the neural level for both text and vision? Like, are they identical mechanisms?
We have to be very precise here. It definitively proves parallel semantic focus. Both modalities understand exactly what evidence is required to solve the problem. But it doesn't strictly prove that the internal circuitry is one-to-one identical, neuron by neuron. What it really shows is that visual pretraining successfully extracts and exposes the reasoning-relevant evidence to the LLM in a format that perfectly mirrors the logic of text-based reasoning.
It's a profound connection either way. Now, I do want to look at Section C of the paper. I always respect a research team that publishes their negative results, because knowing what doesn't work saves the rest of us millions of dollars in compute.
Oh, absolutely. Negative results are good science.
And the obvious thought experiment here is, if predicting a continuous latent representation is good, wouldn't generating the actual raw pixels be even better? Like, why not just force the model to literally draw the next patch of the PDF?
It is the most intuitive next step for any researcher to try, and they did try it. They bolted a MAR-style autoregressive decoder, MAR stands for masked autoencoder for Reconstruction, and a frozen variational autoencoder, a VAE, onto the LLM's hidden states.
So the goal was to take the latent prediction and use the VAE to decode it all the way back to the raw page pixels, giving the model fine-grained pixel-level supervision with a standard mean-squared error loss.
Exactly. And it was a spectacular failure.
Wow.
Adding that generative decoder slapped an extra 300 million parameters onto the model. It cratered their training throughput by 30 to 40%. The entire training run took 1.4 times longer to complete.
Ouch. But did it at least make the model smarter?
Not at all. After burning all that extra compute, the downstream reasoning gains on those math and science benchmarks were virtually indistinguishable from the decoder-free version. The pixel-level loss provided nothing but diminishing returns.
Why do you think that is? Is it because forcing a model to predict pixels means you are basically sourcing it to memorize irrelevant noise?
That is exactly it.
Like, if I'm training a model to understand quantum mechanics, I want it to learn the math. But if I force it to predict pixels, it's suddenly spending compute trying to perfectly reconstruct the specific font anti-aliasing of the PDF, or a weird scan artifact, or the exact hex code of the white background.
You nailed it. A continuous visual latent is a high-level representation. It captures the underlying structural meaning of the patch. But when you use pixel-level MSE loss, you severely penalize the model for microscopic, meaningless variations.
It just distracts the optimization process.
Right. The model starts throwing parameters at typographical noise rather than focusing on the actual semantic reasoning task. The decoder-free setup works precisely because it ignores the pixels and optimizes purely for structure and meaning.
That makes total sense. So let's bring this all together for the engineers listening who are trying to map out their next training run. The core takeaway from this Shanghai AI Lab paper is that visual pre-training on raw documents preserves geometric and structural knowledge that text extraction completely destroys.
And it does so using a fraction of the token budget. You are getting 80 billion tokens worth of scientific knowledge compressed into just 20 billion visual tokens.
Plus, you achieve massive zero-shot cross-modal alignment without needing to curate massive data sets of paired images and text, which fundamentally challenges how we think about scaling laws right now.
Completely. We have spent the last few years obsessed with the idea of running out of high-quality text data. We've been scraping the bottom of the internet barrel.
Right. But if visual latent prediction is this effective at compressing knowledge and teaching logic natively from images,
then the data wall might just be an illusion caused by our reliance on text. The native visual form of scientific documents, technical manuals, and blueprints is just this untapped goldmine of rich, unlabeled supervision signal.
which leaves you with a pretty wild thought to mull over. If we can bypass text extraction and teach a model to reason directly from the visual structure of a PDF, what does the next generation of foundational training look like?
It's a great question.
Could a model like GPT-6 or Claude 4 skip text-first pre-training entirely? Imagine a model whose primary pre-training corpus is just a continuous silent visual stream of the world-absorbing physics, geometry, and structure, natively relying on text only at the very end of the pipeline as a lightweight alignment layer just to talk to humans.
If visual tokens truly are the ultimate zip file for knowledge, the entire text-first paradigm is about to be flipped completely on its head.
So next time you are looking at a beautifully complex diagram in a research paper, don't try to parse it into text. Just let the model see it. That's it for today's deep dive on AI Paper Slop. Keep building, and we'll catch you next time.